Today I will talk about how we develop electrodes in the Nora, focusing on alkali water electrolysis, so not so breakthrough as my colleagues, but this is something that is actually a product, so I hope this perspective is interesting for you. Before this, I will have to give you the Nora overview, of course, otherwise the management will have my head. So we were born in 1923, and we provide technologies for electrochemical, water, and energy industries. So, and we listen to the voice of the customer and make sure that we all arrive to a better future and are part of the green revolution. Just to give you some numbers about the Nora today, or at least what it was in 2024, the numbers that might be interesting for you are about the patents. We have more than 280 patents now, and 5 R&D labs worldwide. The headquarters is in Milan, but we have 2 research centers in Japan and another 2 in the US, in Ohio, one only dedicated to water technologies. And we are spread in 24 operating companies, and we are more than 2,000 people. About our business, as I said, is about electrodes, energy, and water. So we don't only provide products, but also services. The Nora was born, let's say, as an electrode company. So the electrode technology business is the more important for us. So we provide anode and cathodes and the recoating of electrodes we'll see for many applications. But the second sector where we expanded in early 2000s, let's say, is the water technology sector. We were providing the electrodes for that technology, but then we expanded towards the full electrolyzers, and so we provide a lot of also technical assistance and analytical services. And finally, we moved to the energy transition. So we are providing, of course, electrodes, but you'll see also that we have our own alkali water electrolysis system that is called the Dragonfly. And we provide services also there with engineering and supply and maintenance. So we are the largest supplier of method-coated electrodes worldwide, and there are many applications for that. The chloralkali, electronics, and mining are the, let's say, the big fields, but we go from pulp and paper to steel and concrete corrosion, plumbing, automotive, a lot of sectors. And for water technologies, our main applications are for water disinfection of pools, municipal water, and industrial water with a portfolio of different electrochlorinators. But let's go to something that is more interesting for this audience, which is the green hydrogen production. We provide not only electrode and coatings, not only on metal, but also gas diffusion electrodes for fuel cells. But we are also starting to supply our Dragonfly stack. And our main partnership is with ThyssenKrupp Nucera. And every electrode used by ThyssenKrupp Nucera comes from the Nora, as we are part of that joint venture. And as for the coatings, the many families of patents that you saw earlier are mainly about catalytic coatings. So we have our own proprietary electrodes that provide premium performance to deliver a lower levelized cost of hydrogen. So you can see that thanks to our coatings, we have a lot of saving in terms of energy consumption. And our electrodes can be also operated at higher current densities than competitive technologies, resulting in a higher production rate. And of course, the key numbers up to 2024, we already provided 2.4 gigawatt of green hydrogen technologies since 2022. And these years we are producing more than 1 gigawatt additional. And for our small scale green hydrogen electrolyzer, we have in the backlog in the next few years 5 projects to arrive at up to 8 megawatt, mostly funded by the European Union. Something that we are doing that I think is quite interesting, and hopefully we'll be able to show it to you completed, is our gigafactory. In the outskirts of Milan, we are constructing a factory that will be able to produce these electrolyzers and electrodes that I show you. And right now it's under construction. We have a floor now, but this was some months ago. So, okay, how do we develop our electrodes? So we start from the formulation and fabrication of our electrodes, and we'll go through that, how we design that, and then we go through characterization, electrochemical testing in the lab. Then we have some live testing, first in beaker and then in the cells, and then we arrive to production. And all these steps provide a feedback that we use to continuously improve our electrodes fabrication. So how do we design our electrodes? There are many principles that we can follow, that we have to follow. And first of all, we have to look at the operative conditions, if it's continuous or intermittent operation. The intermittent operation is very important since for green hydrogen, since we are coupling the electrolyzers with wind or solar power, we require this kind of operation. And this is very demanding for the electrodes because there are shutdowns without polarization. So we need high flexibility in our electrodes and high robustness. And we have different clients that require different current densities. And if we have high or low current density, we have different coatings that we can apply because let's say that the robustness required and the final lifetime is different. Of course, we need to have a look at the price because we are applying noble metals so far, so noble metals per meter square, and it's very important to make sure that we are competitive against our competitors and make sure that we have less and less noble metal in our roadmap. And we have different geometries, different substrates based on the customer's needs, because each electrolyzer have their own substrate, and we need to make sure that the coating interacts well with the separators, the dimension, the shape. So there is a lot of optimization after we reach the client and know what the needs are. And of course, it's important how the balance of plant and the stack are constructed with what kind of materials, because the different materials will bring different impurities in our KOH, and that will interact with the coating, and we'll need to understand which is the effect on the catalytic coating. And finally, the electrolyzer technology, if it's atmospheric or pressurized, we have different designs. The manifolds can be internal or external. The different number of cells connected have an impact on stray and reversal currents. So we need to design, and you'll see how we do it, different protocols to make sure that we properly manage the shutdowns and understand how it impacts on the coating. Because we might have a very nice coating, but we have to guarantee that it lasts 4 to 8 years. So we need to be extra sure about what we are bringing to the customer. So about our testing principles, which is, let's say, the core of my presentation, from electrochemical testing to live testing, I will focus on live testing. Electrochemical testing, you will see a lot of presentation about that, and it's really about having a good protocol and understanding the activity in the right environment. But live testing in a real electrolyzer is key. So it depends on the kind of operation that we have. If we have, let's say, a continuous operation, well, it's quite easy. We have the anode in its own voltage window, the cathode, they are producing oxygen and hydrogen. But things get complicated when we have a discontinuous operation. Because when there is no longer the polarization, we still have the electrical conductivity provided by the manifolds and the bipolar plates. And as a result, the system behaves like a battery. So gradually we have the two potential moving toward intermediate values. And so the cathode moves towards values for oxygen production and the anode towards hydrogen. And we need to assess this condition that is different with the different designs to assess the electron robustness and lifetime. So, and of course, for each material, we need to study what happens to the material. Here we provide the nickel, which is something that we can disclose, of course. We have a different transition occurring from oxyhydroxides during operation. They convert to hydroxides during discharge. And by studying the chemistry, we are able to further develop the coating. So we are also able to model, thanks to our engineering department, and simulate what happens during the shutdown. So we are able to calculate the reversal current. And this changes with every design and every customer, so we have a lot of simulation going on. And this is very important because we obtain the values that we have to input in our protocols to develop good life testing. And here I report also a study that our Japanese colleagues did by coupling all these studies to a real pilot system of 3 cells and measuring it to see how our modeling was, how good we were. And since we have different clients, different electrodes, different customers, different scenarios, we need a lot of cells. So only for alkali water electrolysis, we have 200 beaker cells with different protocols. And every year, just for alkali water electrolysis, we are able to collect more than 1.5 million of testing hours. And these images are from Italy, Japan, and US. So it's quite spread, and the protocols are shared. And for every beaker cell, we record every signal that works 7 days a week, 24 hours. We record all the signals, all the physical parameters, and then we couple them with the XC2 measurements, so the coating loading and how it's reducing in time, the single electrode potential, and all the characterization. Every hundreds of hours, we remove the electrodes, we do all the characterization, so we're able really to study the deactivation mechanism. So we have a lot of data sets that we are collecting, and we are trying to increase the data quality and our predictions, of course, in different operating scenarios. So here, for example, I provide, this is the data set we have for cathodes, for example, and at some point we are developing the possibility to do some machine learning on these data sets to enhance our prediction capacity. So after the live testing, we have the cells testing. Unfortunately, I do not have a nice picture of our 1 decimeter square cells room, but there are many cells also there. So we are able to have, let's say, a pilot testing before arriving to the customer, because let's say that from the beaker, of course, to the real system, many things can change. So before arriving to the customer with something new, we make sure that we have an intermediate step and years of operation to make sure that we know what we are doing. And of course, this is not only for alkali water electrolysis. This all started with the chloralkali electrolysis, and then we let's say we moved the experience towards the alkali water electrolysis. And finally, we arrive to production. So we have performance prediction with the first 3 steps. Then we have early prediction of lifetime with the electrochemical, the life testing in beaker. Then we arrive to the cell, some predictive maintenance. And of course, from production, a lot of bad feedback can arrive, because we usually coat 1 decimeter square electrodes, and then we have to coat the meter squares. So a lot can happen there. So also that part where our researchers are in the manufacturing plant to see how it happens and learn and go back to the lab is part of our improving continuously. And of course, there is a lot of data historization to continue to arrive to machine learning at some point. Finally, we're right to the field. So it's very important for us to have trustworthy clients that allow us to do field testing and collect more data. And this is the real validation of our tests. So all these thousands and thousands of hours of operation really need a validation from the field, so we can develop better protocols for green hydrogen and for any application.